thank you so much for that kind introduction. Please let me know if anything doesn't work at the moment. And yeah. So allow me to start this talk with a movie. And I mean, I did my PhD close to Hollywood, so I obviously care a lot about movies. And what you see here is actually the first commercial of a robot ever. That was in 1969, so just a few years after the Unimate industrial robot had been introduced and brought into factories. And they were so cocky back then that they directly said, okay, next, after bringing it into factories, we'll bring this robot into people's homes. Now you directly see this monster. Well, obviously, you will not bring this big robot into people's homes. But on the other hand, well, you ask yourself what has really changed. I mean, despite the obvious anachronism when it comes to the societal changes, which are so obvious in this movie still appears, this commercial really appears rather futuristic. But our robots have become better, no doubt about that, right? They don't look like this monster anymore. Quite clearly, we have way more computation, and computation is way cheaper than it used to be. Also, the robots are much cheaper than they used to be. We have way more sensing possibilities, and even the programming of the robot could be done today by any undergraduate student, probably by any high school student. So you would expect that what they program would still be, well, would be amazingly much more advantageous in comparison to back then. But sadly, when you look at it more clearly, you recognize, how did they do this? Well, they took this highly paid engineer to just basically figure out a couple of wire points at the right locations. Well, this part was faked, obviously, with the opening of the bottle, but everything else was just basically programmed by moving from location to location. If any of the objects had been at the wrong location, the whole program would have failed, completely failed. And that's precisely the way of how today's undergraduate students would still program this task as they did back then. Luckily, society changed big time. The housewife who stays at home and has champagne while the husband goes to work, I believe, is a thing, well, from the past. Now, the big question for us, of course, is why haven't we delivered on the robotics side? And it's actually quite sad when you think about it, right? I mean, this is 70 years, sorry, not 70, this is 50 years, more than 50 years ago. So we should be able to long have these abilities. And it obviously has to do a lot with embodiment. But before we even go any deeper, we should maybe ask ourselves the simple question of, well, where have robots actually been successful? And well, there is one obvious answer: car industry, right? For example, there wouldn't be any car production in Europe or in the United States or any other developed country if it wasn't for robots. In fact, even in China today, which we long thought of as the pool of infinite workforce, they had to move in all kinds of industries completely to robotics, and actually quite leading in industrial robotics. What do you do in industry? Well, you adapt your embodiment in a really terrible way, because you make your robot so stiff, so power hungry, that it basically works like a simulation and has an accuracy of 150 micrometers. So it's basically, the world becomes a simulator. And if you would be going into the way of this robot, it would go right through you, because in its simulation of reality, you don't actually exist. So that looks pretty bad. Then you look at the other two examples of where robots have been successful. Well, obviously, there is the lawnmower robots, where typically there's just a wire in the ground, and this it either follows the wire or it uses the wire as a boundary, and does some random changes if it uses the boundary. It uses the wire as a boundary. So again, actually not that much embodied and not that much intelligence per se in it. And worst of all, Well, when you look at it, you look at the Roomba and you get your first Roomba at home, you know the first thing you do is you rearrange your furniture until it finally doesn't get stuck anymore. So with other words, we've only been successful in robotics and real applications whenever we adapted the tasks to the robots. So what should we do instead? Well, quite clearly, we need to adapt the robots to the tasks. And well, what does that require? Well, that obviously brings up the big question, well, shouldn't we actually, well, learn these things? And there's been a trillion successes in, for example, reinforcement learning in recent years. And it makes, of course, it appear super promising that you think like, okay, well, TD Gem, already backgammon was solved in the 1990s, the Atari games in the last decade, the playing Go at superhuman level, and then all of the simulation successes of OpenAI, it appears like, okay, should be around the corner. So should we actually just use reinforcement learning and be done with it? And again, well, learning with the body, which you could either call embodied learning or robot learning, well, is actually quite hard, especially when you compare it to classical robot engineering. Since, I mean, in the end, that's the benchmark we're up against. A classical robot engineer is typically really, really good at his job. And he's really, really good at adapting the tasks to the robot. And so that the embodiment of the robot actually doesn't matter at all. And it is really just, yeah, you turn the robot into a simulation and you don't worry about intelligence. Try not to worry, not to use the embodiment beyond that you actually are realizing a simulator. So that gives us a very tough benchmark when we're getting into robot learning. Then the next part, of course, is data is expensive in robot learning. You cannot just do what you did in a simulator, in all of the different computer games. You cannot do what you did in computer vision, where you downloaded trillions of pictures from Flickr, Google image from Google, and so on. And you can't just take the whole of all texts on the internet and squeeze it into one big network, as people have done in ChatGPT. Since data actually means trials on real systems, and the real systems are different between themselves, and their different situations are so incredibly different that you will never be able to accumulate sufficient data. But you see there in background with this T-ball playing, that was an experiment we did during my PhD. And well, every single trial there means you have to pick up a ball, bring it back, put it back on the stick. And any reasonable learning algorithm, which really learns from scratch back then, needed several thousand trials. Only when you would start with a right kind of inductive bias, you could actually be in any way faster. So big point, of course, then is whenever you say that data is expensive, you have to compete against the robot engineer, then directly all of the deep learning people will tell you, oh, well, if you can't do it on a real robot, then we should learn it in a simulator. And that's also, of course, not a possibility, because if you can learn it on a robot simulator, you don't need reinforcement learning, right? If a simulator is so good that you can do, well, learning on it and use the solution from learning, well, then you can also do planning. And we know that planning obviously scales much, much better than learning, and can give us really, really good solutions. And then, well, any real roboticist knows things break. You will not actually be able to, you'll not actually be able to run a robot infinitely long. And even crazier, generalization and motor control is not trivial. So there's a guy called John Milton who does amazing studies on how stability, stochasticity, and all of these things affect humans. And among others, he figured out a lot about generalization. And one statement I really liked, which he made in a talk, was that golf playing actually doesn't help your hockey. And which is somewhat surprising, right? I mean, you would think that this would actually be quite conducive. But it actually makes generalization very, very hard. And well, then you want to do learning in real time because you want to adapt to to events in real time in real life. And that is something you cannot do if you need two nuclear power stations in order to run your simulators, as so frequently done in the OpenAI experiments. And finally, at some point, we want to bring this on a real robot, which may actually be mobile and not just having access to a cluster behind it. So you may want to have the computation on the the robot itself, or you need to have a real-time communication through some crazy wireless network with mobile phones and what the heck. And you have to maybe do a lot of the computation still on the system. So you have energy and communication limits, which are going to hold down your ability to actually do computation. In other words, robot learning is not a straightforward answer. So what does robot learning require? Well, I strongly believe it requires robotics inductive biases. So what's inductive bias? An inductive bias is an inductive bias allows a learning algorithm to prioritize one solution or interpretation over another, independent of the observed data. Inductive biases can express assumptions about either the data generating process or the space of solutions. And the big questions, I think, which we should be asking is, what inductive biases does robotics offer? And how can we use them for improving robot learning and especially robot reinforcement learning? That brings me finally to the outline of my talk. I'll be talking about inductive biases. I'll fill it during the remainder of this talk. So let's start first with a bon mot. And when I got into robot learning, people told me stay away from reinforcement learning because imitation learning is always easier than reinforcement learning. And the second thing they used to say back then is, with reinforcement learning, you'll never get any kind of a job, because people back then mainly did grid wells. And let's have a quick look at imitation learning. I mean, most people who do imitation learning do actually model-free behavior cloning, which is a surprisingly old method. In fact, the first people to worked on it in the 1960s with the boxes kind of algorithms. And what they basically do there is they take a distribution Q over the states S and the actions A, and they try to approximate it by both inferring a state distribution, here denoted by mu pi, over the states S, and a conditional distribution of actions given the state, which is the policy, here denoted by pi. And already behavior cloning works surprisingly well because typically you introduce some form of regularization, and that gives you actually all kinds of cleanup effects, which result in the student often becoming much better than the teacher. However, of course, if you bring in more knowledge, like let's say knowledge about your system, about how the state distribution is affected by the policy pi and by the model of the system, for example, P, which is also conditional distribution over S prime given S and A. Well, if you bring this in, you actually end up with a model-based behavior cloning, which surprisingly actually hadn't been done since the work of Peter Englert in actually the early 2010s. However, the dual of this problem is very, very well known. The dual of this problem is actually the problem of inverse reinforcement learning, where precisely the dual of this has been used, where a value function then appears, and you get actually a good solution. You can also create more specific duals if you reduce the parametric policy class so that only minimal physics is ingrained into your model. So you're largely model free, except that you require that your system is a mechanical system. And in this case, you get things like motor primitives and solutions which actually can make you learn very powerful without complete model knowledge. Now, I should add, this dual surprisingly people are surprisingly bad. Since if you look already in the Markov decision processes literature from the 1980s, you will figure out what Puterman in this fantastic book of his as has so nicely he put down, is basically that inverse reinforcement learning is harder than model-based behavioral cloning because the number of constraints in there will be quadratically more in versus linearly many constraints in the model-based behavioral cloning formulation. So you should clearly try to favor the model-based behavioral cloning solution over an inverse reinforcement learning solution. Now, let me show you an example of what you can do with model-based behavioral cloning. And in this case, just applied to a minimal physics model of a motor primitive, in this case, a probabilistic one. And you can actually, from just 6 demonstrations, already learn how to play a really good forehand, including all hand-eye coordination, including all of the things you require in order to return the table tennis ball back over the net. Now, 6 demonstrations, and working out of the box, that is very hard to beat by any reinforcement learning algorithm. So why is reinforcement learning so much harder? Because the reinforcement learning problem is substantially different. Unlike before, where we had a notion of data with a function Q, the distribution over states and actions, which we had observed, we have no notion of data in reinforcement learning. And we could again do the same kind of formulation as before, of saying like, okay, we do what people call reinforcement learning by linear programming, for example. And we could then, well, formulate the dual problem again. And this is actually the dual is the model-based behavioral cloning style or policy search style of the problem. You could do the dual problem again, but you get a value function. And that turns out to, well, have no data in there and a rather, hard linear programming problem, especially when it's infinite dimensional. Now, I should add again, most of the time we avoid this in reinforcement learning because, well, we use the Bellman equation, or through Bellman's principle of optimality. We simply say we only favor one action, we solve for the optimal actions, and therefore we can actually change the primal problem with the value function into the Bellman recursion. Again, the primal here is harder than the dual, or the policy search problem is easier than the value function problem. And the worst is we have no notion of data in here. So nearly all of the algorithms we have been using in the past are somewhat made up. So what should we do? Well, that brings me to my first inductive bias. We should stay close to our training data. So what does that mean? Well, we take the reinforcement learning problem, we take the imitation learning problem, and we merge these two together by making one a constraint of the other. And well, we have then basically a constraint problem, which actually has a notion of data and a notion of data in there, and therefore can actually deal with this properly. We came up with this actually really early on, and it took us a long time to really understand how to make it work really well. So I came up with this. The really first well-working algorithms were based on it were only in 2010, but it yields an analytic solution for the policy. It gives you all of the mellow max, soft max formulations. It gives you the entropy regularization methods in reinforcement learning. SAC is an approximation to it, natural policy gradients, natural actor critic, TRPO. They're all basically just approximations to this program. And up to today, this is one of the easiest ways of how you can actually make reinforcement learning work on a real system. So what you see here is Kai Plöger. Kai Plöger managed to teach each robot how to juggle. This year was actually me just dropping by when he wanted to show me his master's thesis. And this year is what you see as the learning process. So he created 400 rollouts with altogether where the robot trained how to juggle. Now I should say this is one arm juggling with the 2 balls. For a human being, that is as hard as juggling 4 balls with 2 arms. And since for us the rhythmic on both arms actually makes it easier in many cases. And including all of the starting and shutting down of the robot, that is 56 minutes of robot experience. I'm pretty sure that none of us would be able to learn how to juggle well with just less than 1 hour of experience. I mean, complete lifetime experience even. And well, the robot system can in fact juggle for more than 30 minutes without failure, where most of us humans would be totally worn out. And we only have to shut it down after 30 minutes because juggling is actually rather energy expensive, and you have to shut it down because of the overwhelming motors. No, I asked Kai, of course, immediately, well, what do you do if you have 2 arms? And I pointed to the other arm right next to his robot. And well, he told me, come back on Monday. And on Monday, he showed me this, where, well, he was capable of using the exact same algorithm to directly learn how to play, well, how to juggle with 3 balls and 2 arms. Pretty much out of the box. So from Friday evening to Monday morning, I don't know how much time he obviously spent in the lab, whether he stayed the whole 2 days or just had a few more hours. So that brings me to that allows me to close the first inductive bias. We should always stay close to the training data, because if the training data is from our embodiment, we will get much better solutions and we get actually a reasonable learning problem. Now, the next important message comes from, well, some extent classical robotics, some extent movement science for human movement science. And it's actually quite interesting. In robotics, most people try to turn, well, robot movement into strokes, so point-to-point movements, while in motion sciences, in human motion sciences, they typically talk about, well, both strokes and rhythmic behavior, and that we have both separately represented. And now that obviously implies a notion right away, since it implies the notion that there should be something like a modularity in our movement. So my PhD student, Rudy Lutikov, back then, he went out and he said, well, what can I actually do if I just have a single long trajectory? Can I actually learn from that something useful? And he looked at many tasks, I should say. He did this in manipulation, he did this in Tai Chi, and obviously he did this in table tennis as well, where he recorded one big long game of forehands and backhands. And you see here, well, this long trajectory and you also see some of the symbols which it directly managed to extract from that one long demonstration. So how would this work? Well, here's the more general picture of that you could have one or many demonstrations. You would over segment these demonstrations, and then you would start to see, well, which of these segments actually is really independent from the other. And you would start to learn a library of primitives from these segments, so distributions over trajectories, these given state distribution over the trajectories. Yes, and when you have then this collection of distributions, as basically one big mixture model, well, then you can decode and you can first of all create, well, a distribution over all the possible trajectories given these symbols, and also select from these and, well, make them work in various new situations. So that brings me to the second inductive bias. You should always use a modular policy structure for composition. You should actually not try what we have been doing in deep learning, where we try to create monolithic policies, which in the end, well, will always be limited by the monolithic structure which we have imposed beforehand, unless we can give it all of the different scenarios as prescribed, well, in near infinite collection of trajectories. So once you have a modular policy, you obviously need to make it work. And well, for that, you typically need to work with both the symbols, you could call them options like Rich Sutton did. Now, the way we use it is slightly different from the way he uses it in options, and you would directly then have a gating network similar to a mixture of experts, which enables you to have, well, many different sub-policies. So what does this imply? Well, it obviously implies that we have to take our reinforcement learning problem from before, and now we have to, well, insert into it at least these options of the gating network, all denoted in red here. That's a very naive extension of the gating network, but it works surprisingly well already when you're now using information also about the opponent, which is quite crucial for deciding whether you can do the forehand and the backhand. And well, you can actually now deal with a variety of different strokes and situations in robot table tennis. However, it turned out that table tennis is actually not such a difficult game when it comes to multiple different symbols, and that the so-called naivete is actually rather problematic. Because if you have two options for, well, doing a forehand and a backhand, for example, and they're equally good, well, in this case, you may end up with a big problem that you will not have primitives or symbols which specialize by reinforcement learning onto these different options. Now, luckily, Chris Daniel figured out the key insight here of that you need another constraint to that problem from before and force your primitives to have only limited responsibility, and that can be enforced by limiting the amount of information stored in the gating network. How does this work? Well, it really forces the primitives to specialize in terms of its behavior. And once you have these additional constraints, well, you try this in tetherball, which is slightly more difficult than table tennis because the behaviors overlap much more frequently. And you could show that this works much better than the naive approach. You could also show that it works much better than an approach which is monolithic. And at the same time, it gave us a principled way for starting with a large number of primitives from, like, for example, Rudolf Ludwikov's type of policies, and then reducing them to, well, the most parsimonious number of primitives, which still fulfills the task. So that basically should tell you, well, we need to use modular policy structure for composition, and we need to be quite smart at how we train such policy structures. Now let's go for the next two inductive biases. And again, you need to start this with the bon mot, since we all know models can be very, very, very powerful. But errors in models are the easiest victims of reinforcement learning algorithms, and they can be quite easily exploited. Now, when I was a young postdoc and I had just been allowed to create my own lab, and there had been a big Max Planck director who said, like, here, Jan, have enough money, however much you need, buy yourself a nice robot and impress me. So I wanted to impress him. I directly did what, well, the wrong thing according to the statement, and I did a model-based reinforcement learning algorithm that worked beautiful in simulation, and I decided to run it on the real robot, and on the real robot it did bang, went right into the joint limits. The robot was destroyed, and I had to go back and say, oh, please, can you give me some more money so that I can actually repair my robot? It wasn't the perfect start. Let's put it this way. Now, what had gone wrong? Actually, incredibly amazing what had gone wrong, since the model, which the model-based reinforcement learning algorithm had learned, was extremely good. It was extremely accurate. But accurate does not mean that it actually reflects the underlying physics in an appropriate way. Since basically by being accurate and well, matching all of the actuator deficiencies of all the little parasitary effects which you have in a real technical system, it had also created a possibility for the reinforcement learning algorithm to take shortcuts which are not physically plausible, where it can basically create energy pumps where it gets energy for free, and it obviously wants to use that. Just on the real system, if it tries to use that, it makes the system unstable and it actually breaks the system. So this has brought my PhD student Michael Luther to the key insight that we actually have to learn in a way that it's always physically plausible. So what he basically suggested is that we create, well, he actually suggested that we explore this complete space between, on the one side, black box models, as we have them, for example, in deep learning, and on the other side, white box models, which basically include all of the physics that which can manually model. Now, he actually proposed two solutions, and they're both really interesting in their own right. One of them requires a little bit more knowledge. That's the differentiable Newton-Euler algorithm, where he literally recorded a data set of just 4 minutes of motor babbling, so random movement, and learned a model from that, but one which at least ensures that Newtonian physics is actually only considered that it can only learn something which actually corresponds to physics by ingraining the right structure into the function approximator. And then he just used again the REPS algorithm from before, relative entropy policy search from before, and learned on the real WEM system. And well, here you see basically the two things which are amazing about this. So first of all, it learns from, well, completely from these 4 minutes. It's of data, and it extrapolates to, well, completely unseen string length. If you look at the Diffnea model of Michael, and it even works for other string length than the ones which, well, he had been originally working with the result that it transfers, well, to different string length, different starting points, different situations, while both the nominal physics model as well as a feed-forward neural network or LSTM neural network both don't give you any transferability, and a very, very, very bad repeatability, or very, very bad success rate, and very bad repeatability. So that went incredibly well. And he really explored this complete space between, well, just putting in a minimal amount of inductive physics, inductive biases, like assuming for the differentiable Newton-Euler algorithm that we have rigid body dynamics and a kinematic chain, which gives you this really high performance for ball in the cup. And you can even go lower and just assume that there is Lagrangian mechanics, which then enables you to, well, learn even more. You could even deal with more flexible items. You can, since you don't need to require a kinematic chain anymore. But at the same time, of course, the learning process is also slower and requires, well, more data for achieving the same kind of accuracy. So key next inductive bias: use physically consistent models. Quick question. I have until 10:30, right? Or okay, as I don't see anybody complaining. The next big question you should ask yourself, of course, is what's wrong about training and simulation? And there we actually have a pretty devastating answer. The devastating answer is there is a simulation optimization bias. That means if you have the truly optimal solution, which is learned on the, well, would be learned from infinitely many trajectories, for example, on a real system, well, this truly optimal solution is guaranteed to underestimate any solution learned from the real system on a finite number of samples. This even has a pretty clear intuition. Intuition is basically you can always make a mistake, which is so bad that you're creating an overestimate for your return at a location of your parameters which is, well, wrong for the optimal one. And so we are guaranteed to be wrong. Now, Fabio figured out that we can actually bound and control this bias. And whatever we do to the mechanics of the system, of the ball, in this case for this ball bouncer, we can fill it with paper clips, we can and to arbitrary perturbations. In all of these cases, it will in the end learn one more general solution, which works not just for one of the different scenarios. So this is, I think, with paper clips or virtual paper, and it will still work. Similarly, you can also do things like taking card pull with different pull length, and you can learn a solution which transfers over different pull length. So that gives us another inductive bias. It gives us the inductive bias that we need to control our optimization bias when we do model-based reinforcement learning. Well, finally, the next one mod is, one from real robotics, one poor lesson all of us who work with embodied systems have learned the very, very hard way. And that is that the fastest way to destroy a robot system is by doing exploration with it. And of course, in robot learning, exploration has a central role. So we need to make exploration safe. And in order to make exploration safe, the key component here is that we basically figure out how to never ever harm the system itself. And here's a key insight when you look at where people hide safety, typically in a robotics problem. And they don't do this like reinforcement learning people who, in the end would create a reward and have the reward take care of safety, since you would much rather want to do this in the constraints, since the real difficulties, if you hide them in the constraints, you can actually ensure safety from the beginning on. So that gives us the next inductive bias. We should definitely always use our constraints to direct our exploration. And my team came up with a really cool solution here. So they always construct a constraint manifold. Then they determine the basis of this tangent space which arises from it. And subsequently, they can sample the state space velocity in the tangent in space and do safe exploration during learning. Now, we tried this in air hockey because we knew that all of the people who have been doing learning before in air hockey either really did bad damages to their table or to their robot. And basically we took actually a big human table, and we only created one hole into this paper thin layer so far. And that was before the safe reinforcement learning process. And we allow the learning system to, only learn safely. And this is how it would look in simulation. And these are all the different behaviors it learned on the real system. Now, I would like you to look especially at the one at the lower, the two at the lower row, since I think they are actually quite impressive in terms of behavior, especially the one to the lower right with the dynamic hitting. And by now we are so far that we have a competition running, and anybody who wants to partake and show his learning solution, that would be our pleasure for you to try. We have a fantastic simulator for it, and it really works quite well. So, but key here is, in order to make embodiments work, we need to put the safety of them required for the body environment interaction into the constraints. That finally brings me to the last inductive bias. And the last inductive bias is one which is the most natural to this community, since it's the one thing you learn when you start skiing or any kind of major sport. And then the teacher at some point says, go with the flow. It sounds like magical. And at some point you realize you go with the flow when you do skiing, and you really let your body go with the flow. And we thought, how do we do this actually for learning? And we decided again to do this in table tennis. And my former PhD student, Dieter Büchner, built a robot, which I had already tried to build myself when I was a postdoc. And he really completed it, and he refined it, and he made it fantastic. And he basically created a system which, can do high accelerations as we need them for table tennis. So we needed needed strong actuators, and we decided to go for pneumatic muscles here with 1.2 kilonewtons. And we apply them to small moving masses so that you can actually, well, still achieve these high accelerations with the system. And in this case, well, we want to do antagonistic actuation because it prevents damages to the robot so that we don't have to hide all of the problems and the constraints. It enables also compliances, and it enables, well, spring damper effects where we can actually release a spring and therefore get a very, very strong impulse response. So this robot, well, it looked really, well, we thought it was really cool. And then came one of the most famous mechanical engineers over from MIT, and he looked at our robot and he said, like, yeah, this may be a computer scientist wet dream, but it's a control engineer's nightmare. So he really tried to crush our spirits, since we had built the system from the beginning on only for performance and learning, and of course never even for a second considered that, well, he or anybody else would want to do this with classical feedback control. Now let me show you though what we got out of this system. And let me fast forward a quick bit. So for training, we decided to simulate the ball. So we took past ball trajectories and let them run until the moment where they would or would not hit the table tennis ball, the table tennis racket with the ball. And then, well, with the simulated system, we executed the actions, and then we gave it this initial policy, which is pure motor babbling. And only after, well, and we simply let it play, and every time where it got a reward, well, by accidentally hitting a ball, no matter where it went, just ready for hitting, it gets a first reward, and a second reward if it gets onto the other side of the table. And after some hours, it manages to regularly hit, and after 14 hours, it hit the simulated ball really well. And subsequently, well, we did the same thing again, but this time with a real ball, which required another 30 minutes. And then it actually does pretty impressive returns, given that this is a system which would defy classical control approaches. And so that brings me to the last inductive bias, and that is, well, you should really bring the natural dynamics into your learning process so that the natural dynamics finally can actually, well, accomplish the exploration for you. And if you cannot do that, then you obviously need to resort into putting it into the constraints. So that brings me to my conclusion. Use these 6 inductive biases. There are way more, of course, but these 6, I think, are really important for when you do embodied learning. And well, with this, I would like to thank you for your attention.
Yeah, thanks for the wonderful talk. So we have quite many questions, but we have limited time. So if you can open the chat, we have like two questions in the chat.
Okay.
Yeah.
So if the robot's morphology could grow or change, how would you account for this? Would it be as simple as adapting the manifold of the robot's workspace? No, I think the question of morphology and learning, this interplay is a super interesting question, but I think it needs to go at 2 different timescales. And we should also differ between, how to put this, big changes and small changes. So adding a joint in a kinematic chain, for example, could be a very natural thing, which could be between, I don't know, let's say hundreds of trials. And we could probably try to introduce this into the same system. And that could actually be a very, very successful way of quickly developing, well, co-developing learning algorithms and co-developing in morphology with a learned policy. On the other hand, I think sometimes it would really be the coolest to create things which are totally separate. So where it's not just you make a few links a little bit longer and shorter, and you add a few and you add a joint here and there, but where you actually really go for, well, completely different forms of morphology. And that, I think, requires that there's a much slower process around it. For the first one, I'm pretty sure that this process is actually mainly that if you look at different skeletons and you recognize that how similar even a crocodile, or actually most amazing is, the sperm whales are descendants of a goat. So you recognize you can change the morphology of a goat to go back into water. Right? This is just stunning, and these are small parametric changes, right? Like the first time. For the letter type, I think it would be much more important to study the letter type where we really evolve things which aren't in the basic building plans. So splitting something off like insects and mammals split from each other. So something which is fundamentally different. But that requires a totally different time scale, and learning algorithms are definitely not up for that interplay yet. And I think this would be a really cool thing to do projects about, but which is still highly underappreciated. So then there is the case studies all assume that states are observable or not. How do you think about long, complex, hidden states? So one thing which arises quite naturally by these information theoretic solutions is that the compression of history, that basically memory is an action. Therefore, it arises quite naturally. So far, we have only been using it in the context of tactile sensing, where in the end you need to compress this large number of incoming, very noisy data into actually, well, much more suitable for actual control. But I agree with you. Obviously, we focused when I started out, we always focused on being largely observable, and we've reduced it only very slowly. So like in table tennis, when we started using human data, for example, well, we clearly didn't get all of the observable, but we actually had to the hidden state of the human had to be inferred. How you could see from the arm trajectory what the human actually wanted to do. All of these things became problems the policy had to solve on the way.
Yeah, and just like a quick question, like you didn't mention much about the sim to real gap, and many researchers are kind of working in this direction. Do you think it's something fundamental, or we can get around this problem?
So I think, well, there is a fundamental problem in it, because we simply know that that basically a bad model can arbitrarily mislead us. The key thing is that we also know that we will never have good models which also give us good extrapolation power, right? And typically when your model becomes more and more accurate, well, you also lose your ability to extrapolate because you need to put it better and better into data. So you automatically have, in both cases, huge biases, and controlling these biases is really key. But I think this is a problem we can actually handle, and I strongly recommend looking into Fabio Muratore's work, since he really made some fundamental contributions here, which haven't totally been appreciated by the sim to real community so far.